go through session 7 today, but before we get to that, we need to cover a couple of things from session 6. And I apologize for any issues if you already did these homework problems. I was trying to at least not have the last one due, but I should have also made 6 and 7 delayed. So I'll go in and I'll just make them due tomorrow. All right. If you did them already, great. If not, I'll just change them. But for the latter part of session 6, what we're going to talk about are Poisson's ratio and a general approach to solving problems in mechanics, along with an indeterminate problem. So here, let me make this full screen and maybe hide a few things. Okay. We've all taken a rubber band, hopefully, well, maybe not all of us, but what would be a natural material that you would find in the wild? I don't know, maybe a leaf? That's actually not the greatest, but something that's elasticy, spongy, maybe a sponge, all right? And you pull on it, right, and you notice that it shrinks in its cross-sectional area as you pull it apart. Similarly, if you push on the ends of such a rubbery material, what you'll see is that it gets larger. Okay? So now this relationship between strain that we apply axially and the strain that we witness across the cross-section or laterally is given by a ratio that is unique to these materials, or the material that you might be studying. And this ratio is called Poisson's ratio. Okay, so a stretched material will have its lateral or radial dimensions shrink or decrease. A compressed material will have its lateral or radial dimension expand or grow. And we can give a ratio, by the Poisson's ratio, but first we have, which is down here, but first we have a way of describing the longitudinal strain. Okay, so this is the strain in the direction that we might be pulling or pushing. And we also have a way of describing the lateral strain, okay, which is given by this delta prime divided by, say, a radius. If it's a rectangular cross section, we'll just use the x or the y dimension. Okay, so it would be the cross section's width or the cross section's height. Now, again, what we're looking for is a relationship that describes how this strain in one direction relates to the strain in its cross section. Okay, so axial strain relating to lateral strain, and it has a negative sign. Okay, because as we just said, right, I stretch in one direction and then it shrinks. I push in this direction and it gets bigger. Okay, so I'm decreasing, and if I'm pushing right, I'm decreasing in the axial direction, but the lateral direction is expanding. Now, we're going to be saying that this ratio is also good in the elastic regime. And here is maybe my poor attempt to draw what might be happening. So let's say that you started with a large cylinder, something like this, and you pulled it so much that it became a much smaller cylinder. And we can think about what the change in the length might be. So change in length would be delta here. The way it's drawn is delta over 2 on either side. And we can also look at this change in radius, okay, as being something like a delta prime. And there's maybe a little bit better direction, but a better drawing, okay, and also to show that the same behavior is true if you have a rectangular cross section, okay. But in this case, we're going to say we have some change in the y dimension, Okay, so in that direction, and some change in the x direction. Now, the radius, right? It's kind of fun. The radius is all all symmetric, essentially, right? It doesn't really matter which radius or which radius you take, which of all those that you can choose. And in here, right, you want to just be a little bit more careful about the x and the y. Okay. Yeah, so in this case for the cube, all right, what we have are these changes, all right, in x and y, all right, which are potentially given by this kind of 2 delta L, okay, over L. And the change in the z, you could say, okay, it's also given by 2 delta L, so all these delta L's, and the 2's cancel out, and so once again, we have this ratio between the strains. Strain in the z direction, strain in the x direction, okay? These are going to be related to each other. Now, what are common values of these? Well, we mentioned this before. Common values. All right, maybe I'll jump over this. Okay. Oh, no, I do need to talk about this. All right. So let me just add a slide here. Or maybe I must have them somewhere. Did I not put them in? Whoops. Okay. So common values for Poisson's ratio not good. Not good. What is going on? Are about 0.3 for the metals, so aluminum and steel. And for materials that are incompressible, okay, to conserve their volume, they're typically close to 0.5. And if you're doing simulations, what you do is you pick a value like 0.47 or 0.49. You don't pick 0.5 exactly, because it actually leads to an anomaly or a singularity. This is not good. Okay. Oh, okay, that's good. I got a little bit of control. Sorry about that. All right, so common values would be 0.3 for, say, steel. And you might see things like 0.2, but somewhere between 0.2 and 0.35, all right? And for rubbery materials, it's 0.5, and this would be for a rubbery material, so like those silicones. And typically, we don't use 0.5, but we use 0.49 or something like that. Okay, and that's because there's a singularity. Where does this singularity show up? Okay, it actually shows up oh yeah, okay. Oh, I'm so scatterbrained today. Okay, or right now. All right. It actually shows up in the next section, in the next slides. All right, right here. Okay, so this is what we'll talk about this in a second. All right, this is the bulk modulus, but you see that in there, and a couple of things, and also in transformations, you'll see this 1 minus 2 nu. All right, so that little v-looking thing is what we call nu. So we simple nu, okay, and that's the Poisson ratio. So this actually, it makes these quantities explode. So we don't, in mechanics, we don't typically use 0.5. We'll try to do something very close to it. Okay. Now, okay, so those are pretty much the two values you need to know. And for this class, pretty much it's going to be 0.3, okay, or 0.33, whatever it is. All right, but we'll give it to you. So that means, what does that mean? If you go back to what we've defined here as a ratio, okay, let's go back to say this equation. Okay. So this is 0.3, right? Which means that if I pull by a certain amount, okay, elongate it, okay, the lateral dimension is going to shrink by 0.3 times whatever that amount is in terms of strength. Okay, so that's good. And you can kind of get an idea, right? If I were interested in having conservation of volume, okay, then, and I just said, okay, that means that nu is 0.5. So if I pull it by a certain amount in this direction, that means that the x, for example, would go down by 0.5, and or it would be 0.5 times that, and the y would be 0.5 times that. Okay. So that's the Poisson's ratio. Now, it turns out that it cares not so much about which direction you apply the axial load. What am I talking about? I mean, we care actually, but Poisson's ratio doesn't. Okay, we definitely care, and we're going to show you why we care. But I can pull an x, okay, and if I pull an x, then I get shrinkage in y and z. If I pull in y, let's call it, no, maybe y, okay, then I get shrinkage in z and x, all right, and if I pull in z, all right, I get shrinkage in x and y. Okay, I think my hands were kind of doing that right. Okay, so this makes our thoughts about Hooke's law for axial strain interesting now. Because what did we say? We said sigma is equal to E epsilon, right? And that's true if it's uniaxial. What does uni mean? One axis. All right. But what happens if I pull in this direction, right? But I also pull in another direction at the same time, right? If I, it's going to want to, they're going to want to fight each other. Okay. So like pulling in this direction, right, that means it's shrinking here and here, and so that's fine. And it doesn't really affect the strain in this direction. This is still sigma equals E epsilon, if I'm thinking about the strain in the one in one direction that I'm pulling. But if I have a pull in an orthogonal direction, at the same time that I have a pull in this, first direction, then my strain is coupled, okay? And the way we think about this coupling, all right, is kind of as follows, right? So let's say that we have a strain in X, okay? So the strain in X, if I were pooling in X, okay, would just be sigma X over E, right? That's just Hooke's law. Everyone see this? This to this is just Hooke's law. Okay. Now, if there are no pools in the other directions, in the sigma and the Y and the Z direction, then I'm done. But if there are pools in the Y and the Z, okay, then there's an effect in the X direction. And that is given by the minus nu times sigma Y over E, right? So what you have here, these are all Hooke's laws, but just in 3 different directions. Okay, the ones on the right. But then when I start to think about the strain, I have to account for the pool or the stresses in the orthogonal directions to the strain at which I'm interested in. Okay. Does this make sense? Okay. So when you can start, and this is for normal stresses. Okay. We haven't talked about shear stresses and things yet. Okay, which we will, in terms of how it shapes our infinitesimally small element, right? Because what we just also did, right, is we said, oh yeah, these are big boxes. Okay? But we've actually inadvertently, well, not inadvertently, we have purposely thought about these boxes also at the infinitesimal scale. So you have this type of behavior at an infinitesimally small element throughout a structure. Okay? But if it's a large structure that's like a cube, right, that's just like the infinitesimally small one, except the infinitesimally small one, right, is going to have effects from the neighboring cubes. Okay? But for this class, we try to stick to what? Simple structures, right? The normal loading in bars, the shafts, the beams, right? And when we get to the beams, right, we're going to be looking at combinations of normal stresses and not normal stresses. In the shafts, we don't even think about, well, typically we don't think about normal stresses unless it's also combined with a load that's pulling the shaft axially, right? But we're just talking about bars and normal stresses here, essentially. Okay, so another way to write this exact equation is as follows. And this is something you want to write on your formula sheets as well. Okay? And if you like matrices, I like matrices. Everyone says linear algebra is beautiful. I don't know. But at least I like useful matrices. Okay? And just how is this useful in case you're not up on your matrix multiplication? Okay, you go row times column, right? And I will give you the first component over here. Right? And if you forget, right, you just look, this is the actual, I would write this, definitely write these 3 on your formula sheet, and if you want to be nerdy, write this one too. Okay? But this is row times column will give you the second one, right? Second row times this entire column, and this third row times this column will give you the third component there. Okay? So that's Poisson's ratio. And for the homework that you did, okay, you calculated out how much shrinkage you would have in a orthogonal direction. Okay, so now here is a general approach to solving problems in mechanics. Now, why did it take us this long to come up with a general approach? Well, you already had a general approach for statics. That approach was equilibrium, equilibrium, equilibrium. Okay? But then we said, hey, look, there's a whole bunch of problems that are indeterminate. Remember this? You solved a bunch of determinate problems using equilibrium. But now if we want to use, if we look at problems that have more unknowns than our equations of motion or static equilibrium equations give us, then we have to do something else. And this is the something else. Okay? So if you have deformable bodies, all right? Which we do. And you think about 3 steps. The first step is equilibrium. Okay, so you're like, okay, well that makes sense. I got that. Okay. And sometimes, like, I had this wonderful teacher when I took mechanics undergrad first time, and she would draw 3. She would like kind of divide the chalkboard into like 3 sections sometimes. Okay. It's not always this simple, but equilibrium was definitely one of those sections. The next is compatibility or geometry, right? So we've talked a bit about geometry. And this might be something like keeping track of boundary conditions, right? And remember when we said, the delta of A to B plus the delta of B to C is equal to the delta of A to C, right? That's kind of what we're looking at. Right? So geometric compatibility could be something as like, hey, this displacement here or this displacement there, it's 0. Right? And then the third, essentially Stokes' law. Okay? Those are the constitutive equations that we have. Okay? Or it could be the modified version, right? But this is true for uniaxial loading, right? This is true for uniaxial loading, right? But now I just said, like, you can have the Poisson ratio, and that adds these minus nu sigma over E terms, right? But these are the 3 things. So if you're stuck on a problem in mechanics, all right, draw all these 3 columns. You'll have ample paper, I hope. I'll give you the paper, okay, actually, just so you know. And you will be able to kind of try to think, what's going on with the geometry? What interesting constitutive relationships do I know that might be applicable here? And you can also lump in, if you want, like F equals K delta, right? That's another constitutive equation. Okay, it kind of comes out of this, right? But that's a constitutive equation that's useful. Okay, now. Yeah. All right. Okay. So, for example, this was using, okay, what we were talking about with, okay, sigma is equal to F over A, okay, and that's a constitutive equation, but it's based on force, right, and displacement, right, it's based on geometry, and so what we're saying is that, okay, I can write epsilon equals F over EA, and then I can write that delta is equal to L times epsilon, and then we can write that we have phi. Okay, which is what we talked about in our last meeting together. Okay. Now, here's an example. All right, if we have a bar with an elastic modulus and a Poisson ratio, okay, has a length. What are the lateral strain, change in radius, change in diameter? Okay. So we can use kind of this approach if we want to say, okay, well, here's equilibrium, there's an internal force F. Geometric compatibility, we can say that the diameter is equal to, or change in diameter is equal to 2 times the change in radius. That's probably one of my big mistakes, careless errors that I make. Okay, please be careful of that. And then constitutive equations for stress, for strain, and like we're talking about the Poisson's ratio. Okay? And so we can now write out these relationships and come up with some responses. Okay. And this is assignment. You already did this. If you have a load where it changes in all directions, okay. If we apply forces now in the x and y directions, right? So this is what do we do here? Equilibrium, geometric compatibility, constitutive equations, and now these are the larger constitutive equations that we can use, and so we can figure out what the change in lengths might be there. Okay, I'm going pretty fast through this because I think you probably looked at some of these examples already. Okay, now this problem is a little bit interesting, okay? And I think it's worth talking about. This is not any different, okay, than going back to, I think, when did we introduce indeterminate systems? This is, this is just the bar, right, that we were applying a load to. In the middle, there's some F, okay, and then we can say, oh, we're actually going to add another side to it. Okay, that's all this is. And there are a couple ways to look at this, but I think it's probably useful to use superposition here. Okay, so we're going to use. So let's think about this in terms of. All right, I have equilibrium over here. We have geometric compatibility. And we have our constitutive relationships over here. Okay. So here I'm going to suggest that we use superposition. Okay, and that will be applicable in both geometric compatibility and equilibrium. Okay, so we'll say, okay, we can use superposition in both of these. Okay, and how would we say? What would we do? We would first. Okay. Oh, and I guess I should say, what is it that we actually want to know here? We're interested in figuring out the effective spring constant. Okay. Oh, this is. Okay. Okay. Relating F to delta. Okay. So what we need to know, like they're giving us F, but we need to figure out what delta is. Okay, because we want to know. All right, we want to know. K, or yeah, K. Okay, at location D. All right, and so that is going to be given by F equals K delta, right? There's a delta here, and there's an F there, right? And that's also kind of a general point, is that typically when you're thinking about an effective spring constant, the displacement is where you're applying the force. Now, you could do a different problem where it's not, and you can have, like, if I had this bar without something over here, and I said, hey, I'm applying a force here, and I want to know what delta is here, and you could have a spring constant relating to them, but that's a little bit atypical. Okay, so and this is what we want to know. So the question is, for this, what is delta? Okay, that's because I know F already. So if I know delta, then I can figure out what K. Because then K will just be, right? So I got to figure out the delta. And to do that, let me suggest that we approach this problem with superposition, like we did before. So what does this mean? This means that I can apply, I'm going to apply this force F here, okay? And I'm going to apply this restoring force R at the right side, okay? And if I'm thinking about now superposition of geometry, okay, let's say that I have that top case, right? I'm going to say that, oh, there's some geometry, we'll call it delta 1, or some displacement there, right, due to this applied force. And I have also if I draw in this direction, which is okay, delta 2, okay, I'm going to have some displacement delta 2 at that location, right? And from geometric compatibility, my big time delta, what is it going to be equal to? Yeah, delta 1 minus delta 2 here, right? Assuming that the way I've defined it is that delta is going to the right. Okay. So I've got my geometric compatibility, and now I gotta go back and think a little bit about my superposition, or my equilibrium, but superposition with equilibrium, right? So here, this is where having a little more space is useful, right? But here, let's just draw this out, right? If I take a cut, ooh-wee, that's really bad. That's also very bad. Okay, so if I have a cut there, right? Everyone see that's a slice? And this is for the top one. I know it's kind of silly, but what is the internal force? It's just F, right? So it's just F. Okay. All right, now I'll go over to my constitutive column, and I'll be like, oh, well, if I know the internal force here, then what is delta 1? Well, there are a couple ways. You gotta be a little bit careful here. I'm going to put this under the constitutive category, all right? But I'm going to say that delta 1 is going to be equal to this F over what I'll call K1. Do you see that? So now I'm defining. I'm going to come back over here. I'm not going to redraw it all the way, but I'm going to say that there's a K1 over here. Okay? And K1. What is K1? Can anyone tell me what K1 is? This is also a constitutive relationship. Remember how to define K1 for a bar? Or not K1, but do you remember how to find the effective spring constant for a bar? Yeah, look back at your notes. You want me to do this on Monday, all right? We got time. You can learn a lot of things. 4 days. 5 days. What do you think K is for a bar? Yeah? Yes! All right. Okay, in the house. All right, good. Caveat. Okay, now you tell me though, what am I using for my E? Well, they told us that the elastic modulus of the constrained bar is just 74 gigapascals, right? So it's going to be 1E. All right. Now it's confusing because there's a position E as well. All right, there, but this is the E for the bar. We'll just call it E bar. Okay? So E bar. Okay, what's the A? Well, they tell us the cross-sectional area, right, is here. We'll call that A bar. Okay, so we'll call that A bar. All right. And what's the L? L1, good, right? It's just L1. Okay, everyone see that? Critical thing, all right? So now we figured out what delta 1 is. That's nice. Okay. We have more geometric compatibility stuff here, right? In that the this so let's call this delta E1, all right? And then we've got, if we put it this way, delta E2. Okay, everyone see what we're doing here? So we've got a delta E1 plus a delta E2, right? Has to be equal to 0, right? Or if our delta E1 minus the way I've drawn them, right? It has to be equal to 0, right? So delta E1, delta E2. Okay, so now, all right, I know actually that delta 1 is equal to delta E1. So I can even write over here that delta E1 is equal to delta 1. Okay, you see this? And what is, and I have some R, right, here. Okay, so I have a, well, what is delta E2 going to be equal to? What is delta E2? Yes. Okay. Yeah. Okay. Yeah. In the. Yes, that's true. Okay, that's fine. Now, can you tell me what it is in terms of a force? In terms of R, this reaction force. R over K. Yeah. Okay. And let's R. Okay, so R over K. Good. All right. And what is? But let's call it K2. Okay. Let's just call it K2 because we're interested in a K, right, which is the F over the delta, and that's being defined here. All right. So let's call it K2. So we're going to have an R over K2. And what is K2 going to be equal to? Right. Okay. So the E bar, A bar over L1 plus L2. All right. Okay. And you're right, okay, in that you also said that delta 1, right, all these guys, now I'll write out what you said, okay? This is equal to delta E1, okay? And so what does this allow us to do? All right, it allows us to solve for R. Okay, so we solve for R. Okay, and then once we solve for R, okay, then we've got to figure out what delta 2 is. What is delta 2? Okay, this is interesting. Well, I think it's interesting. You may not think it's interesting, but I think it's interesting. Okay, so look at this. If I take another slice, okay, for this bottom one, I'm going to have an internal R. That R is the same across. Okay, and it's in compression. Okay, now if I'm interested in how much this is going, right, we said that we had this delta 2. Okay, so we have a delta 2 here. right, which is also drawn over here. Okay, we also drew it over here. Okay. So this delta 2 is going to be equal to this R, right, over what we called K1, because the spring constant is just for that region. Right? This is maybe a little bit counterintuitive, but there's a bunch of R's all through here. Okay, but remember, it's the internal force that dictates how much it's going to move. Okay, so delta 2, okay, again in the constitutive column, is just going to be R over K1. Okay. So now we can figure out what delta is. Delta, we go all the way up here. Delta, we said, was delta 1 minus delta 2. Right? Delta 1 is F over K1, and delta 2 is going to be R over K1. All right. And then we can calculate out what K is. Right? So the overall K, right, was just going to be the force over this delta. All right? And so that's how we can use this kind of three-pillar approach to being able to attack these types of problems. All right? This is maybe the most complicated problem that we've done so far. And I didn't want you to do it now. Now, you could have done it differently. Yeah, you could have done this. You could have done this problem differently. You could have, for example, figured out what the internal force here might be. Okay, and using some of the other techniques, using our superposition, right, and then gone that route. Right. This is not the only way to do this problem, but it's a way to do it using these three pillars. Right? And so this concludes what we were going to cover yesterday. All right. Okay. Now we'll move to session 7. Any questions before we move to session 7? Yes, Andrew.
Why does delta E1 equal to delta 1?
Okay. So why does delta E1 equal to delta 1? Okay. So because what's the force in this member? At least when we did superposition, right? The force, remember we're looking at this problem just with the force being applied at the middle, and there's nothing on the right end. The force in the second region is 0, right? So that's why delta E1, which is just along for the ride, is equal to the same delta in the middle. Okay? Because that particular second half here, it doesn't experience any stretching. Right? Once we've gotten rid of the constraint on the right. Okay. Of course, in reality, right, it does. And we can think about that in terms of, the superposition if we want, right, of having this reaction force in R. Good questions. All right. Okay, so let's move on to session 7. Okay. All right. Yes. Reminder: exam 1 is on Monday, and it's going to cover through normal loading 2, which is what we're going to have for half of tomorrow. Okay. And then after normal loading 2, we move into torsion, right? So I figured that this was a good breaking point for exam 1. Okay. And we just covered this, so this is a review, right? Now we're going to talk about something that leads to the bulk modulus, which actually we foreshadowed just a few minutes ago. Okay, and we're going to think about volumetric strain. So this is not I don't know if I've written a problem that's really made high use of volumetric strain, okay, on an exam, but it's nonetheless, how do you say it? It's an important concept, okay? And I guess indirectly, yes, we have used questions that use volumetric strain, but maybe not so directly. Well, first, what do you think volumetric strain is? What does it sound like? Yes?
It sounds like the whole thing expanding or contracting.
Yeah, right? Okay, so up to this point, we've been thinking mostly about, okay, you stretch in this direction, and maybe nothing happens in the other two directions right before we introduce the Poisson ratio, but in reality, we know those are going to be contracting. But we've been thinking, okay, one direction, two directions, three directions. And we're going to use that same mentality, but now we're going to apply it to a change in volume. So if we have a box and it has sides dx, dy, dz, all right, like so, then the volume of that infinitesimally small box is dx times dy times dz, right? Does that make sense? Now, we apply normal stresses to the box. Okay, sigma x, sigma y, sigma z. And let's say if they're all in tension, what happens to the volume of that box? It expands, right? It's going to grow. And you can see we have, so there's supposed to be a smaller box, right? And then the larger box there. And thank you whoever created that open source figure. What are the change in lengths? Okay. Well, the change in lengths can be thought of as just epsilon times the initial length, right? That would be the change in length. And what is the new length? Well, that would be the original length plus the change in length, right? That would be the new overall length of a side of the box. So another way to write the original, right? The original would have been, say, dx. And then if I have the change in length, right, that'd be dx times epsilon x. So another way, right, this is really dx plus dx times epsilon x. So those are the new overall lengths in the x direction, the y direction, and the z direction. All right? So 1 plus epsilon times the d whatever direction, okay, or like you see there. So now we have an initial volume, right? And we can think of a new volume, right? What's the new volume going to be? The new volume after I apply sigma x, sigma y, sigma z is going to be this length times that length times that length, right? It's just because that's the volume of a 3D prism, okay? So, and in this case, if it were a cube, right, they're all the same, right? But it's the length times width times height. So the new volume we can write as the original volume plus a delta V, okay, like that, is this big mess. And the change in volume, okay, would be just delta V equals this big mess, or maybe that mess, or this mess minus V naught. Everyone see that? That's what the change in volume is. And what is V naught? Well, V naught is up at the top, dx, dy, dz. Okay. So now we have this expression. Okay. So just copying this orange one on the right and then minusing the V naught right there. Okay. And if you do a little bit of algebra, okay, you get that for these small strains, okay, this quantity in the brackets right? You can kind of see that, right? 1 plus 1 plus 1 plus is approximately just epsilon x, epsilon y, epsilon z. Okay. You can apply, if you really want to check it out, you can do FOIL a couple times. Right? You can do FOIL on this, first, outer, inner, last, of course. And then you can group, this will be a polynomial, right? And you can group two of them together, and then you can do FOIL against that one. Or you can use whatever, distributed law, whatever you want to do, right? So you're going to see that there's going to be like some like epsilon cube terms, epsilon squared terms, right? And the square of a small thing is a smaller thing. The cube of a small thing is a smaller thing. So we can approximate those as dropping out. And this is what you get. Okay. Now, dilatation is an expression for volumetric strain. That is the definition of volumetric strain. It is that you have the change in volume divided by the original volume. Okay? And what do we have here? Well, now we have expressions for the change in volume. Okay, it's approximately this job here. And the original volume, which was dx dy dz. Well, look, what does it mean? It means that this expression divided by dx dy dz just leaves us with epsilon x plus epsilon y plus epsilon z. At least for me, this is a little bit counterintuitive. Okay, but because of the smallness of the parameters that we have here, right, this is what happens. Because if you were to ask me, I'd be like, oh, should it be like, maybe like epsilon x times epsilon y times, I would think some type of multiplication, right? I mean, which is absolutely right. We did multiplication, right? We did 1 plus epsilon x plus 1, right? We did the multiplication out for the volumes. But in the end, the change in the volume divided by the original volume is just epsilon x plus epsilon y plus epsilon z. And I mean, it's also maybe a little counterintuitive because you're like, wait, if I had like, x dimension plus a y dimension plus another z dimension, right? That would just be units of length, right? And that's not cube, which is what you normally have with a cube, right? But again, these are dimensionless parameters, right? The epsilons are dimensionless, so it doesn't matter. Okay. So now, what happens here? You're like, oh no, oh no. We started with these stresses, sigma x, sigma y, sigma z, right? And we have now, we did essentially a bunch of geometry, okay, up to this point, right? This was like geometric compatibility up to this point. And we also, we have, this is an equilibrium because we have these stresses and we have cross-sectional areas, right? It's not accelerating. So we've kind of done those two, but now this brings in the constitutive nature of things. Okay, so now with the constitutive relationship, we have a relationship we got to by geometric compatibility or from geometry, and we can multiply them out, or we can add them up, add them up, and when you do this, all right, what do we see? We see that we get the following. All right, so this is a relationship that, again, is not something that rolls off of my tongue, and I'd be surprised if it rolled into an exam, okay, in this form. The next slide, okay, is a little bit more possible, okay, but dilatation by itself like this, I think it'd be a little bit, I mean, it's cool. It's fine. I guess I could ask the question, what's the volumetric strain if I know sigma x, sigma y, sigma z, okay? And I know E and I know the Poisson ratio. Okay, that's cool, right? But yeah, it's not. And again, right, remember what we said? If, this is another cool example of Poisson ratio equal to 0.5. Remember we said for the rubbery materials, the volume is conserved? Well, look at that. E is delta V over V naught, right? And if this is 0.5, then this is 0. So no matter what I do to the stresses on that piece of rubber, I still have the same volume. Okay? Whereas if I have a piece of steel or a metal material, that number is 0.3, okay? And so I'm going to have a change in volume. My volume is not conserved, okay, when the Poisson ratio is not 0.5. So here is a little bit more, and introduces a term that we call the bulk modulus, okay, or the volume modulus of elasticity. Okay, so right, you have, and this comes up a lot in, well, where does it come out? It comes up, yeah, it comes up in solid mechanics, right? We're bringing it up. I usually think of it more in terms of acoustics and things, but it comes up. It comes up. And the bulk modulus, all right, essentially is a ratio between the pressures that would be applied hydrostatically. Okay, what does hydrostatically mean? It means I put a piece of material in an atmosphere, okay, or I put it underwater, and it has the same normal pressures acting on all 6 sides. If it's a cube, right? But if it's a rock, right, with some interesting shape, right, it's got all this pressure acting on it. Okay, so in this case, P is equal to minus the normal stresses. And so now you're like, oh, this is interesting. I've now connected my solid mechanics to, those old problems in physics where we said, what is the pressure, right? What is the pressure acting on my ears if I am 10 meters underwater? Okay. Turns out it's about 1 atmosphere. So every 10 meters you go, you got about another atmosphere on top of you. In air, on our planet. Okay. So that's rho GH as a reminder. Okay. So in this case, we can write out the dilatation, okay, in terms of pressure. Okay, so where does this come from? Well, look, we did it here. We had sigma x, sigma y, sigma z. There are 3 of them. They're negative, right? P, right? You see that? And so now we have this equation, right? This is how you would write it if you're under pressure. Again, put it on your formula sheet, but this is not one that, or maybe put it on your formula sheet, but this is like if you were to wake me up in the middle of the night and ask, hey, what is the dilatation as a function of pressure? I would not be able to tell you this. And even some of these others, I'd have to look them up, quite frankly. Okay, so the bulk modulus, all right, is given by this K. It's a parameter. Okay, so this is, I don't know if it's clear, but bulk modulus is K. So like, why? You already have K's for springs. Yes, that's true. Okay. But that's the parameter that's typically used. Elastic modulus is a big E, all right? But this is the, I guess I should try to make this more. That is the bulk modulus, okay? So now, all right, so minus P times V naught over delta V, right? What is this V naught, right? V naught over delta V. So it's the initial volume divided by delta V, which is the flip of the dilatation. Okay? So you see this is delta V over V naught. This is, all right. Anyway, that's what it is. And I mean, that kind of makes sense, right? Because you have F equals K delta. If I tell you what, I ask you what K is, right? Then it's the force divided by a delta, essentially, right? So I got a flip of the volume. Right, that's the bulk modulus. And so K can be related to, right, so you see this, K can be related to the elastic modulus and the Poisson ratio. Right? And this is what I was talking about, I was thinking at a second ago. If you put in 0.5, K explodes. So for rubbery materials, typically when you're running simulations or whatnot, you put in 0.49. So it's a big number, but it's not a tremendously big number that you can't use in your computer simulations. Okay. So that's a formula to write down. You know, why is it useful? You're like, this is cool. Like, someone measured, or I'm looking at a table and it gave me bulk modulus instead of elastic modulus, and I know what the Poisson ratio is, so like I can go between them. Yeah, okay, this is why it's cool. But it also allows us to relate the volumetric strain to pressure. Okay, and so this is another equation that comes up. So P equals minus KE. So this one's a little more common. Okay. And the units of stress, are gigapascals. Okay, so that's fine, and the units of pressure are also going to be in pascals and things, right? Yeah. So just as a note that if the nu gets close to 0.5, things explode. All right. Here are some values. What's interesting, okay, is that for some, like if you have aluminum at 0.33, the K is actually pretty close to the E. And steel, if it's a little bit lower, okay, drops a little bit, but you can kind of generally see that these are in the ballpark. And as we said, with the silicone rubber, or with the rubbery materials that are compressible or incompressible, their volumes conserved, they have a nu, a Poisson ratio that's close to 0.5, and so that causes a huge surge or a much larger K. Okay. All right. And you know, so if we go back to this and you say, hey, okay, dilatation. Wow, that's interesting. So like a piece of rubber and a piece of aluminum, right? They're going to experience about the same amount of volumetric dilatation, right? The delta V over V naught for a given amount of pressure, even though they're very different materials. Okay. So yeah, so here, if just briefly, actually, let me see. We can drop a block in an atmosphere, okay, whether it be water or whether it be air, but if it's pressurized to 100 atmospheres, that's a lot. Okay. And so it's asking, what's the change in the volume of the cube, and what is the change in length of one of the sides of the cube? Okay, what would be the equivalent depth underwater to get to 100 atmospheres of pressure? So there's actually, there's a collab that will do all this for you if you look. All right, there is a collab there, but we can say, oh, we're interested in this. We know that this is the bulk modulus, and we start applying the pressures, and we are going to say we're in equilibrium. We have geometry, constitutive equations. So here, I mean, this is just words. The equilibrium is that we have pressures acting on all the surfaces, and that we're going to assume that the forces on these surfaces are essentially all the same, or the pressures are all the same. It's not accelerating. And for geometry, we can say, oh, well, I'm going to define my dilatation, and I'm going to say it's got to shrink. All right, it's got to shrink because I've got normal forces acting inward, or normal pressures acting inward, normal stresses acting inward. We can say for constitutive equations, we've got our dilatation formula, and we've also got a relationship between pressure and the bulk modulus. Okay? And if we're looking at the change in the volume, we can say that's going to be a manipulation of our equation for dilatation, and we can relate that to the pressure, we know that E, the dilatation, is equal to epsilon x plus epsilon y plus epsilon z. Okay, we derived that a few slides back. And since this is a cube, epsilon x is going to be equal to epsilon y is going to be equal to epsilon z. So that just means that we have 3 epsilon x, okay, is equal to E. So this is another kind of, interesting parameter that pops out, is that, what we said before, like, okay, we can add 3 of them together, but if it has equal dimensions on the 3 sides, it's just 3 times the linear strain. And so this is interesting in that we can now think of the relationship between the linear strain, okay, and the dilatation, as we've got here. We can figure out we know what the dilatation is by pressure, the original volume, and the bulk modulus of the material. Okay, and so we can figure out what the lateral strain is, and we can also figure out, if we know the lateral strain, we know what the change in length is if we know the original length. Okay, and if we want to know the pressure, how deep we are, so we've figured out the change in volume, or you can figure out the change in volume from this. You can figure out the change in length from this, and you can figure out how deep underwater you are from this. Okay. And one of the problems on the homework is pretty much identical, but it has different parameters. And you can, again, use the Colab and calculate it out if you so desire. Just be careful, right? An atmosphere is, I guess I can write it out here in the corner, but 1 atmosphere is 101.3 kilopascals. Okay. So as you're doing this, that's probably one of the conversions you want to keep in mind. And of course, you've got kilopascals, you've got gigapascals, right? Just, we got to be, got to keep track of all of these things. So the Colab will do that for you. Okay. And there it is. That's the Colab if you're interested. Okay, so here's that 101.3 kilopascals, so times E3, for example. All right. It's there as well. This is the 10 to the 9th because it's 68.6 gigapascals. Okay. All right. Yeah, and then there's that's the same kind of thing. Interesting. Okay, I pulled up the slides with the solutions in them. All right, well that's fine. You can take a snapshot, I guess, but it's really just the same thing. All right, this is a slightly more complicated version of fleet. All right, what am I talking about? Okay, well, I'll probably be more obvious in the second one, just when we talk about the rest of this. But do you remember that for a bar, if we have a uniform force acting along that bar, we can figure out what its displacement is, right? By using the force times the length divided by E, or the elastic modulus divided by its cross-sectional area. Okay, that's the formula. But what happens if we don't have a uniform force along the bar? Or what happens if we don't have a uniform cross-sectional area along the bar? Okay, it's like, I don't know, it's some kind of interesting object. Maybe it's a pipe that's changing its cross section, and you have a fun function for it, or maybe it's a portion of, maybe it's a cone or something, all right, that has a linear function for its cross sectional area. These parentheses, x's, it's not clear, all right, but what it means is that they're a function of, okay? So this means this is a function, all right, this x in here, p is a function of x. A is a function of x, not p times x. Okay? So just to make that clear. I'm sure there's a better way for me to draw this or write it out. Maybe if I use LaTeX, it would make it look that way all automatically. But anyway, it is what it is. Okay. So if we just talked about pli, all right, let's look at this equation. And I'm not going to derive it here, but if you're interested, and you know, for the record, the suggested textbook is any one of Hitler's mechanics materials books. All right, just so you know. Okay, so if you're like, I got gaps, I don't understand this. Really, I think that his books do a great job. I think that it's up to like, I don't know what edition. That's a lot of editions. I think maybe 12 editions. Okay, anyone will do. So remember this problem. You've got a cross-sectional area A. You've got a bar with some length, and you've got force, you know, being applied to it. If I want to know the change in length of this bar, I can use, well, I could use the PL over EA that I knew previously, or I can use this new function, okay, this new equation, right? And I've said it, I've hinted at it before. When we think about the displacement, and we did it actually in that 3-column example a few minutes ago, where we were looking at the indeterminate bar, right? We often think of relating displacements to not the external forces, but the internal forces. Okay? And this equation, that P is an internal force. Okay? And it will say it in a second, but I'll just emphasize it here. Okay, the P, this is internal force. Well, that's fine because we know how to cut and slice and dice, right? Okay, so here, if I were to write out something, maybe I would say this is a constitutive equation. I don't know, but it's also, it has, you know, it's fine. It's this equation, okay, just written out. And in order to use it, I need to know what the internal force is. Okay, so the internal force is P, as we've drawn it here. Okay, and we're going to assume in this case that these P, whatever, it's constant. It's constant across. We're also going to assume that the cross-sectional area is constant, right? So P as a function of X is just P. A as a function of X is just A. Okay? So what do we have? We have an integral of P over EA. P is a constant, A is a constant, E is a constant, okay, dx going from 0 to L. Well, the integral of a constant with respect to some parameter and then going from some 0 to some of that length, right? The integral of a constant is just that constant times whatever whatever that variable with which I was doing the integral, right? So that's just going to be px right, over EA, and then I go from 0 to L, so it's PL over EA. So we already knew this, but now we have a new equation that if you want to watch the YouTube video by Professor Rust, or you want to look in Hitler's book, and you can see that derivation. What happens, well, so why is this useful? Why is this useful? They're like, we don't even know how to do this. This is useful, of course, when the internal force is not constant. Okay? If the internal force is a function of x, then we can use this equation to figure out what the overall displacement is. Or if the cross-sectional area is changing as well. Okay. So let's look at a more complicated example. All right, and let's just focus our attention here on this drawing for a second. What we're saying is that we have some force, an internal force, that is equal to m times x. Okay? And we had to define, this is, it's very important that you define where x is equal to 0. So we're defining x is equal to 0 at the left side. So p of 0 would be 0. P of L, right, or p at x equals L, which was where b is going to be ml. Okay, so we have this. If we want to draw it out, we have as a function of x from 0 to L. Oops, I overdrew. Right. This is equal to ml, and this is equal to 0. Okay, so that's what the force looks like along the bottom. Now, we're going to do, we could pick a different case. We could pick a reaction force of something, or not reaction force, or we can do different boundaries. But let's just say that there's no force acting on the left side. Okay, so really this problem now there's an R2. This problem has really become the following. Okay, and it's going, and there's a P. All right, there's a distributed force, okay, acting along it. Now, you notice if P is in units of newtons, M is actually in units of newtons per meter, right? Because it's got to work with the x that has dimensions of meters or length. Okay? So if we have this force across the bar, okay, in a distributed fashion, if we want to figure out what R2 is, there are a couple ways to do it, but one way to do it is to say, I've got my R2 on this side, and I just go a little bit over here, okay, a little bit over there, like that, and I've got my P, and my P over there is equal to ML. If I'm infinitely close, right to the right side, everyone see that? If I'm infinitely close, if I'm right up to the right side, I've already figured out that my internal force P is equal to ML there. So that by balance, my R2 has to be equal to, that's just P, is my R2 has to be equal to that ML. Okay? So now, I figured out R2, and I've got some interesting internal force. Sorry. P, this is, I said it's an external force. Okay, that's important. So P is an external force. Okay. It still applies, okay, here, because this is an external force that's acting. So I have an external force here, okay, and these are balanced out. Okay. So if I were interested in an internal force, the F internal, that would be 0. That's not right either. That's not right either. But it's not, I mean, I can write that internal force, but the internal force, okay, the external forces are the same here, essentially. So P is equal to ML R2. No, 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 no. No, 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 no. 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 Okay. Let's not think about this way, okay? Because this is yeah, this is a, okay, this is, I'm sorry, this is not the best example. Apologies, all right? The next example is more standard, okay? This one is kind of an interesting thought experiment, but it has some weird behavior, I think, okay? But what we're saying is that we have an R2 and we have a P of L is equal to ML, okay? So this is the reaction force on this side. Now when I do internal equilibrium, all right, I do draw, okay, this Fi like this, okay? And it does in fact equal 0 at the right side. So it's not bad, it's just, I think it's a little bit confusing because I'm saying that this is an external force. At any rate, we have an Fi plus this quantity Px, right, which is the external force being applied across it, minus R2, which is equal to ML. And so the Fi is equal to M times quantity L minus X. So the general approach to these problems, right, what's the point? The point is that we want to use this new equation that we have. The general approach is to say that we have an internal force and we're integrating it up. Yes, Andrew.
Oh, why is R1 equal to 0?
That's because I said it was. I specified it to be equal to 0. Okay. So there's no constraint on the left side. Now, yeah, this is fine. This is fine, but it's just, I'm sorry, I butchered the explanation. Okay, so now the geometry, okay, we said that we're defining the x as 0 on the left side. The constitutive equation, all right, is that one that we have, the p integral of p of x dx over e times a, all right, and but a is a function of x, so a is constant here, all right, and the internal force here is going to be this one, m times L minus x. And if we integrate it, okay, what we get is the following. Okay, that the delta, okay, is going to be equal to minus ml squared over 2e. This, the reason why, anyone know why I put the minus sign here? Again, this is not necessarily the most obvious point. Yes?
I think it's because you specify the positive direction for x to the right and the change in size is going the other way.
Right. So if I had drawn Fi coming out, like we often do for our conventions, right, then I would be able to leave, well, then I would have a negative sign here, right, and I would be able to leave it as is. So be careful here. It's often better to make sure that you have a force, even though I didn't do it that way here, to have the force coming out of the surface. That's our convention. Any questions on this? Yes.
You just chose the internal forces to go that direction, like that was just all by choice.
That was, and it's not the best choice. Okay, is what I'm trying to say.
But that's a section car, right? Like that piece
Mhm.
is, okay.
Yeah, so what I'm saying is, what I should have done, okay, to be more clear about the convention, okay, it would have made, to keep things simpler, I should have drawn Fi like this, okay, and I have my P of x, and I have my R2, right? I have my P of x, and I have my R2 acting like this. And so really my equation would come out to be Fi is equal to minus, it would be essentially Fi would be equal to, is that right? Yeah, it would be the flip of this. Okay. All right, and then from this, I've got my delta is equal to the integral of P over EA dx. Okay, but in reality, I'm not using P. Also, poor choice. I probably should have used something else. It's for that external. Not really. What I really want is integral of Fi over EA dx. Okay. Note to self, fix in fall 2024. All right, so it's not so confusing. Okay, got any questions on that? Okay. So this is, this next problem is more of the standard one, okay, that you'll see. A very complicated way, all right, of saying hang a bar on gravity. We can say axial deformation in a bar with distributed load. All right. All this is me holding a bar and gravity acting down on it. So this one is a little more intuitive in that here's the bar. I'm interested in the displacement. When I take away that top wall, I have a reaction force. What's that reaction force going to be? It's just the entire mass times the gravitational constant. It's the weight of the bar at the top, right? And this is analogous to what was on the previous slide, where we said, okay, you've got this force that's incrementally growing, linear, okay? That's what's happening in this bar as well. Think about it. The force down here, right? If this bar is under a distributed load, distributed force, the force, like if I just come up a little bit over here, infinitesimally close to the bottom, that internal force is 0. Okay? Because it doesn't, gravity could only be acting on an infinitesimally small displacement, or this distance, sorry, not displacement, and or thickness. And so there's no internal force, right? But as I move up the bar, right, like the force right here, it's got all this bar below it, right? If I'm halfway up, then the internal force is going to be half the weight. When I get to the top, it's all the weight. Okay? So this is more intuitive because it's actual real sense. The previous slide I was trying to make an abstraction using a fictitious linearly varying force. This is linearly varying and it makes more sense. Okay? But what is kind of wild, right, is I need to think when I go to internal equilibrium about what is called a distributed force. Okay? So this is pretty intuitive, right? The reaction force at the top is just the total weight. And I can think of that total weight in terms of a density times length times area, right? Times gravity. Does that make sense, right? We know from high school physics, if I have a density and I have a volume, which is just LA here, and then I can come up with a mass and I multiply by G. So that's all good. It's less intuitive once we have a distributed force and we're doing internal equilibrium. Okay? What it essentially comes down to is a relationship that is going to be a density. Okay, so you can kind of see this, right? You can see it here, rho g LA. It's essentially a density. This little f, this distributed force F, is going to be a density times a gravity. Okay, or an acceleration, better said. Let's call it acceleration. Either way, times a cross-sectional area. Okay, this is what we call a distributed force. Okay, and this is manifest right here. Here's the little f, there's the big F. I need to relate them. I relate them with an integral. So I integrate all these little distributed forces up. So the rho GA, density times acceleration times cross-sectional area. And that's what I have at every slice. Gives me this equation, rho GAX. So instead of rho GLA or rho GAL, instead of having that, I have a rho GXA or rho GAX. This is a pretty important concept actually for the homework as well, okay, which is due tomorrow. Then you have a density times acceleration times cross-sectional area. So now, if we do the internal equilibrium, like we have here, and we define x equals 0, right? So this is an internal force P. Again, a little bit, last time, right, I used Fi, but the equation itself is the integral of P over EA dx. Right? So P is not a bad term to use here. So P is this internal force. We have the R, and we have actual, this is an external force. So I drew just a little f there, right? But it's actually an external force, right, that results from that little f. And that external force is this integral right here. So the internal force P is equal to rho GLA minus rho GAX, which is this term right here. So this is very similar to what you saw, right? Where we instead had an M last time. Now we have rho GA. Okay, that's the distributed force. That is the density times acceleration times the cross-sectional area. That's the distributed, that's the little f. So now, we can say, okay, the delta L is equal to delta at L. We can say that the constitutive equation that's of interest is this one. And we can then just put this guy into there. Okay, and remember, this is not times x, these are functions of x. Also confusing, all right? And now we have that. Whoops. That was it. We could do this integral, okay? And this is a famous expression, rho g L squared over 2b. Yes, Andrew?
Had you the internal force equation on the bottom?
Yeah, here. Yeah. So this is saying at a particular location, right, I've got to get balance, right? But remember, it's like just external equilibrium, but I've now done the method of section, so I've sliced it. So I've got on this system, right? Essentially, I've got a big, you've got this little f, but it's really like, what is the let's put it this way. What is the big F, right, that I have? So I've got, oh, sorry, it's drawn the other direction. It's the other direction because it's acting downward. Sorry. This is the big F, like that, right, acting downward. Right? So if I'm closer to the top, yeah. If I've got the entire thing, then I've got the entire force, right? If I've got the whole thing, so that force is F. So this is the entire external load. Okay. So like if I have x equals L, that's the entire force, okay, from the mass of the entire object. If I'm at the top, right, then I just got this. But what's counterintuitive, like I was talking before, the internal force is at P, right? So when you're at the top, right, it's supporting, there's an internal force that's supporting the entire thing. Okay? But this big F is that expression that we have, which is the integration of this 0 to x times rho g a dx. Does that make sense? So that's how the equilibrium plays out. Good. All right, so there's Colab if you want to use it, and then there's this problem, which I highly suggest that you look at the exam 1 from 2015. Okay, and these this is accidentally I pulled up mine with the solutions, but anyway, you can find there that when you have this windmill spinning, okay, the acceleration, and now we're this is on Earth, but the acceleration due to spinning is much greater than that on Earth. Okay? So what you end up looking at is an expression, once again, where it's density times cross-sectional area times acceleration. Okay? And when you do that, you'll find that the internal load, okay, that you have is going to be the internal distributed force is going to be the density times the area times the acceleration, okay, which is given by this quantity right here, omega squared times tau minus x. The farther out, it's a little bit different than what we were talking about with gravity. In this case, the acceleration is highest, okay, when you're at the tip. Right? That's when the acceleration is the highest. Okay, because that's when it's spinning around there. But the force, the internal force is going to be highest when you're near the middle, because it has all that blade that has to support it. Good. All right. So that's it. Blast. I wanted to go to the lab again to allow you all to do your single experiments, but I went late. So I guess, do you have any questions or anything to cover? We might finish a little bit early today. good.